Injection molding is the most common method for mass manufacturing plastic products. Examples include chairs, toys, cases for consumer electronics, disposable cutlery, and my favorite, Lego bricks. Injection molding was invented to solve a problem for billiards. In the 19th century, billiard balls were composed of ivory harvested from the tusks of African elephants. This devastated the elephant population, so a billiards manufacturer offered a $10,000 prize for a replacement for ivory. And this spurred John Wesley Hyatt to develop one of the first plastics, celluloid, to create billiard balls. He patented an apparatus for molding products from celluloid. This apparatus was the birth of plastic injection molding. In principle, injection molding is simple. Melt plastic, inject it into a mold, let it cool, and then out pops a plastic product. In reality, injection molding is an intricate and complex process. An injection molding machine has three main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it rams forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute. The mold opens and the part is ejected. The mold then closes and the process repeats. All injection molded objects start with these plastic pellets, which are a few millimeters in diameter. They can be mixed with small amounts of pigment called colorant, or with up to 15% recycled material, then fed into the injection molding machine. Before the mid-20th century, injection molding machines used only external heating of the barrel to melt the plastic before a plunger injected the molten material. But because plastic conducts heat poorly, the temperature was uneven in the barrel. Either the middle was too cool and not fully melted, or the outer regions were too hot and degraded the plastic. The solution was this: the reciprocating screw, often regarded as the most important contribution that revolutionized the plastics industry in the 20th century. In the earlier plunger-style machines, plastic filled completely the cylindrical barrel. But as I showed you, the plastic was not at a uniform temperature. The reciprocating screw overcomes this in three ways. First, in modern units, the plastic fills only the space around the shaft of the screw. This eliminates the cooler central region, leaving a thinner, evenly heated layer of plastic. Second, the screw has flights that wrap around the shaft. As the screw rotates, the flights transport the raw material forward through the barrel. The flights also serve to mix the plastic. The screw action agitates the melting pellets within the flights to create a uniform mixture. And third, the screw action itself heats the plastic throughout. The shaft's diameter increases along the screw so that the distance between the wall and the shaft decreases. The flights then squeeze out air as they move the plastic forward, and they shear the pellets and press them against the barrel's wall. This shearing creates friction and so heats the plastic throughout. This screw-induced shear supplies a majority of the heat needed to melt the plastic, between 60 and 90%, with the rest from the heater bands. The molten plastic flows past the front of the screw through indentations or flutes. When there's enough plastic to fill the mold at the front of the screw, it rams forward like a plunger, injecting the plastic into the mold. The plastic cannot flow backwards because when the screw pushes forward, a check ring is shoved against a thrust ring to block the backwards movement of the molten plastic. This forces the plastic into the mold. Initially, the cavity image is filled with air. As the molten plastic is injected, it forces air out of the mold, which escapes through vents. These vents are channels ground into the landing surface of the mold. They're very shallow, between 5 and 40 microns deep. The plastic, which has the consistency of warm honey, is too viscous to flow through the narrow vents. To speed the plastic solidification, coolant, typically water, flows through channels inside the mold just beneath the surface of the interior. After the injected part solidifies, the mold opens. As the mold opens, the volume increases without introducing air, which creates tremendous suction that holds the mold together. So at first, the mold slowly opens several millimeters to allow air to rush in and break the vacuum, and then the mold quickly opens the rest of the way so the part can be removed. These precision machined steel molds can cost hundreds of thousands of dollars. Removing the part from the mold can be difficult. When the plastic cools, it shrinks and so becomes stuck tightly on the core half of the mold. Molds have built-in ejector pins that push the part off the mold. The ends of the pins sit flush with the core half of the mold, but are not perfectly aligned. Sometimes they protrude or are indented slightly. So, if you look closely, you will see circular ejector pin witness marks on molded products. For example, this chair, on its bottom, has an array of witness marks. When the part drops from the mold, an operator has to remove the sprue, that section of plastic that connected the injection unit to the mold. Sprues are manually twisted or cut off the part. Sprues are attached to objects only in molds that make a single part at a time, like a chair. Smaller objects are made in multiples in a single mold. In these, the sprue connects not to the part itself, but to a network of distribution tunnels called runners. The runners fan out from the sprue and connect to each cavity in the mold via a small, typically rectangular, entrance called the gate. You can see the gate on plastic cutlery. The parts for model planes typically come still attached to their runners. Molds always have at least two parts, and where the parts of the mold meet is called the parting line. Here on this piece of cutlery, you see the parting line along the side of the fork. When mold halves close, they are never perfectly aligned, nor do they have sharp corners. This creates a noticeable parting line on the molded object. Another very important aspect of mold design is the draft angle. If a part has walls that are exactly 90 degrees, it will be very difficult to eject because its inner walls will scrape the core half of the mold. Also, the vacuum will be difficult to break because air cannot readily enter. However, if the walls are slightly tapered, even just 1 or 2 degrees, it becomes much easier for the part to be removed because once the part moves slightly, the walls are no longer in contact with the core half and air can rush in. One impressive example of injection molding is the Lego brick. You can see the injection point in the middle of a stud, but this is not from a gate or a sprue. The Lego molds use hot runners. Hot runners are a heated distribution network. This keeps plastic inside the runners molten while the plastic in the mold solidifies. This leaves no gates or sprues to be removed. The molded bricks are ejected, ready to use. The downside is that this setup is more expensive than a traditional cold runner system. On the bottom edge of the brick, you can see ejector pin witness marks. And what's most clever to me is where Lego designs their draft angle. The outside of a Lego brick must be square. So if you cut a Lego brick in half, you can see that these inner supports are thicker at the top than at the bottom. There's a draft angle of about 1.5 degrees. This helps the ejector pins push the brick off the mold. The core half and the cavity half of Lego molds are designed so that the parting line is at the bottom edge of the brick. This hides the parting line. Look around you and see how many injection molded objects you can find. Likely the device you're watching this on has injected molded parts. You should be able to find ejector pin witness marks and parting lines, but you may find something like this. It's a date wheel that shows the month and year the item was made. These are created by removable inserts and can be changed out for each run of the mold. They're very useful for tracking down defects. So to return to where this all started, John Wesley Hyatt and his injection molded billiard ball did not win the $10,000 prize. His celluloid billiard balls didn't bounce quite right. But he did pioneer plastic injection molding, a thriving, continually evolving manufacturing process which creates many billions of products every year. I'm Bill Hammack, the Engineer Guy. To learn more, click on this video overview of injection molding. And this video explains how the molds are manufactured. Click here to see an injection molding machine produce plastic bottle caps very rapidly. Finally, this video details the production and automation of Lego bricks. And to learn the full story of John Wesley Hyatt's celluloid billiard ball, listen to the podcast from 99% Invisible, which I've linked to in the description for this video. We're very grateful for our advanced viewers who critiqued early versions of this video.
Sign up to be an advanced viewer at engineerguy.com/preview.
Thanks for watching.